Namaste and a very good morning to all of you. My name is Mithun, and in today's presentation, we will be looking at a machine learning technique to model patients respond to different drugs. But even before I show you this particular machine learning technique, I'd like to introduce you to the data set that we have. I have information about 200 patients. We also have details about their demographic details like age, a patient's gender, and past medical case history like what is his or her BP level, cholesterol level, sodium concentration in the blood, and potassium concentration in the blood. By taking the ratio between sodium and potassium, we've been able to derive a new column, which is Na_K. The last column is very important because this shows which drug did the patient respond to. For example, the first patient, she is a female, her age is 23 years, sodium concentration in her blood is 0.79, potassium concentration is 0.03, she has high BP, high cholesterol, and the ratio of sodium to potassium concentration in her blood is 25.35, and she responded to drug Y. The second patient with a different set of details responded to drug C, third person responded to drug C, and the fourth person responded to drug X. What is the sample size in this data set? As you can see, the sample size is 200. Using the demographic details and the patient's medical case history, we want to identify the profile of patients who are most likely to respond to a particular kind of drug. Why do we do this? We are doing this because next time a new patient comes, by identifying the new patient's profile, we will be able to recommend which drug he or she should consume. Now, in this particular data set, I have the drug variable, which will be the dependent variable, and all the other variables will be my independent variables. Since I have a dependent variable, I will be calling this as, I will be using a supervised learning technique. In the case of supervised learning technique, we have a dependent variable and a set of independent variables. In the case of unsupervised learning technique, we don't have a dependent variable. And to model this kind of data, one of the best approaches that we have is what is called as a decision tree model. So we will be using a decision tree model to study the pattern of response to the drug. What are some of the distinct advantages of using a decision tree model? There are 5 advantages of using a decision tree model. First, a decision tree model is a non-parametric approach towards modeling. A decision tree model is best suited to model non-linear patterns in the data set. 3, a decision tree model can handle mixed data type. When I say mixed, what I mean is you can use scale variable or categorical variables. Irrespective of whether it's a scale or a categorical variable, a decision tree model will be able to handle both these data types. 4, a decision tree model is easy to use and apply. 5th, a decision tree model is not just a modeling technique, but in many cases, a decision tree model can be used to derive new features and new columns. Suppose the independent variables show a lot of intercorrelation. Whenever there is a lot of interrelationship amongst the independent variables, many times regression will not throw stable model coefficients. But when the independent variables show a lot of interrelationship, decision tree model can and is preferred as a suitable modeling technique. Last but not the least, when your data has a lot of missing cases, when there's a lot of noisy data in your data set, what you can do is you can use a decision tree model because a decision tree model can handle missing cases as well. Now, with this being the background, I will be using a decision tree model to model patients respond to the 5 kinds of drugs that you are seeing: drug Y, drug C, X, A, and B. I can go to the option Analyze, choose the option Classify, and when I scroll down, you see the 5th option from the top, which is Tree. We can use this particular option for our data set. The moment I click on Tree, a new dialog box opens up, and here you can see the dependent variable as drug. And when it comes to independent variables, I have taken age, gender, BP level, cholesterol, and sodium to potassium ratio. What is the method that we will be using to grow the tree? It is what is called a CRT. CRT stands for classification and regression tree. It gives a binary split. Let me click on the option OK. In just a few seconds, SPSS output window pops up, and you can see the decision tree here. For better visibility, let me double click on the decision tree. Let me zoom this in so that we can see what the decision tree looks like. Yes. So the top box here is what is called as the parent node, and it is giving me the distribution of different drugs. 12%, approximately 12% of the patients responded to drug A, 8% responded to drug B, 8% of the patients, again, historically have responded to drug C, 27% of the patients have responded to drug X, 45% of the patients have responded to drug Y. So this is what I learn when I look at the decision tree parent node. When I scroll down, right below the dependent variable, you see a variable which is Na_K. It is nothing but sodium to potassium ratio in the blood. Now, there are 2 divisions here. Either the sodium to potassium ratio can be less than 14.8, which I'll round off and say 15. If the sodium to potassium concentration is less than 15, that is one case. The second case is sodium to potassium ratio is greater than 15. So what we see here is this is a very, very informative and a very powerful node, because whenever the patient's sodium to potassium ratio is greater than 15, they've always responded to one drug, namely drug Y, because you see 100% of the cases fall under drug Y. When it comes to drug A, B, C, and X, their share is 0%. So in future, when a new patient comes and we look at the ratio of his sodium to potassium concentration in blood, if it happens to be greater than 15, straight away we can go ahead and suggest drug Y. But what about those patients whose ratio of sodium concentration to potassium concentration in the blood is less than 15? Here you can see none of them have responded to drug Y. They have responded to some of the other drugs like A, B, C, or X, but predominantly they have responded to drug X, because 50% of the patients have responded to drug X. But this piece of information itself is not sufficient for me to make a decision. I'll have to look at the next variable, which is BP level. So the first important variable is sodium to potassium ratio. The second important variable is BP level of the patient. Now, when you scroll down, you see 2 classes here. Either the BP level can be high or it is not high. Let us first study sodium to potassium ratio less than 15 and the BP level being high. You can see within this class, 60% of the patients approximately have responded to drug A and 40% of patients have responded to drug B. This is another rule that we can pick up, that if the patient's ratio of sodium concentration to potassium concentration is less than 15 and his BP level is high, he is most likely to respond to either drug B or drug A, but predominantly B. I will not be suggesting him drug C, X, or Y, because historically we have seen none of the patients have responded to drug C, X, or Y. So this is how a decision tree in simple rules, in a very, very simple and easy to understand fashion, is able to convey very, very profound insights. Now let's look at the other category. This category represents those people who either have a low BP or a normal BP. If you scroll down here, we are studying specifically low BP level. How did we arrive at this node? You have to trace the path back. Please look at the path. Sodium to potassium ratio is less than 15. BP level is low. If a person has this kind of a profile, approximately 53% of patients have responded to drug X, 47% of them have responded to drug C. Let us look at another class of people wherein people belong to the normal BP. Almost all of them have responded to drug X. So looking at this decision tree, we have arrived at very, very important rules. The first being, if the sodium to potassium ratio is higher than 15, we can go ahead and recommend drug Y. That is the first big takeaway. If I scroll down and look at the next big takeaway, sodium to potassium ratio is less than 15 and the BP level is high. What happens here? If the BP level is high, people have mostly responded to drug B. What happens to the third rule? Those patients who have a low BP level, they have responded to drug X, and those patients who have a high BP level have responded to drug X here. Now, these results are very, very useful, and you can use a lot of these results to suggest and recommend drugs for future patients. But what is the accuracy of this decision tree model? Can I trust this model or not? Now, when I look at the risk estimate is a good indication of whether the model is good or bad. The risk estimate that I am getting here is 0.16, which means that when you use a CART method, that is a classification and a regression tree method, out of 100 patients, 16 out of 100 patients are likely to receive the wrong drug, which also means that 84% is the overall accuracy of the model. 84 out of 100 patients will be administered the right drug. 16 out of 100 patients will be receiving the wrong drug. So this is the message that I get when I look at the risk estimate. Now, let us also look at some of the other important information here. This is the variable importance graph, and this graph becomes very, very important for me to classify which of the variables are most important and which of the variables majorly drive response to a drug. As you can see here, right at the top, you can see sodium to potassium ratio. The longer the bar, the higher the importance. Shorter the bar, lesser the importance. That is the simple way of interpreting the graph. So the first most important variable here is sodium to potassium response. 30% is the weightage that is assigned to sodium to potassium ratio. The second most important variable is the BP level of a patient. Third is cholesterol. Fourth is age, and gender does not play a big role in driving patients' response to the drug. So this feature importance table is very, very important, and it helps us understand which are the key areas that I need to focus on. Let me look at the overall classification metrics. Along the row, you have 5 different drugs being listed. This is the observed category. And along the column, what you see is the predicted category. So I am most interested in these diagonal elements running from left top to the right bottom, because they indicate the correct classification. Diagonal elements always indicate the correct classification, and the off-diagonal elements always indicate the incorrect classification. So let's look at drug A. Percentage is 100%. Now, I do know that this is a very small data set. I've used barely 200 cases, and I also know that I've not split the data set as training and testing, but this is just for the sake of demonstration. Ideally speaking, in a real-time scenario, you might want to split the data as training and testing, build the model and training data set, and then go on to apply the model on the test data set. But for the purposes of demonstration, I wanted to keep it very, very simple. Now, in this data set, what do we observe? we observe that when it comes to classifying drug A, my model is 100% accurate, which means 23 patients who have earlier responded to drug A have been correctly assigned the drug A itself. So you can see here the off-diagonal elements are 0. So in identifying those patients who have responded to drug A, my model is 100% correct. My model is also doing a good job when it comes to identifying drug X and drug Y, because I see 100% accuracy here. Where my model is not doing that good would be drug B and drug C, because those patients who have earlier responded to drug, this is the observed category. So this is drug B. So those patients who have responded to drug B have been classified as drug A. So this is a misclassification that we are able to see. So in classifying drug B, the model is not that accurate. I can say the same about drug C as well, because those patients who had earlier responded to drug C, all of them have been classified under drug X. So when it comes to drug B and drug C, the model is not trained appropriately. And the overall percentage of accuracy here is 84%. So with this, I have come to the end of today's presentation. In today's presentation, we were able to build a decision tree model to identify which is the drug that a patient responds to. We built a model called a CRT, or classification and regression tree. We saw some of the important benefits of decision tree, like it can handle mixed data type, it's a non-parametric approach, it's easy to use and apply, it helps us in feature engineering, it can handle even missing cases. We were able to look at the variable importance chart and come up with interesting conclusions based on that. Finally, we looked at the risk estimate and the classification metrics. With this, I would like to thank my audience for watching this video. Please do subscribe to my channel and share with your friends and family members. And please don't forget to hit the like button. Thank you very much. Have a great day.